interesting. Okay, so we're very happy to have received the proposal from Hyeonbum at ZKProof 6. It was reviewed and accepted, and so you made it all the way here to present the security of Nova on recursive proof systems. Thank you very much.
Thank you for introducing me. And I'm going to talk about the Nova IBC. As you know, Nova is the well-known IBC scheme-based folding scheme. So this work is collaborated with Jae Hong-seo, and let's bring it start. And I consist this presentation as the 5 sections. The first is the IBC and Nova, introduce the concept of the IBC and Nova briefly. And next, I will show the noise sound but posable IBC. From the IBC scheme, I have to point out the limitation of IBC knowledge soundness in currently uses. And next, and third, I'll talk about the analysis models for group-based scheme because of due to the not too detailed in this section. Yeah. So in third section, to analyze Nova in AGM, we briefly consider the analysis model in group system. And next, I introduce the zero testing hash function, which is the weaker condition than the random oracle. And finally, I show the Nova knowledge proof in AGM without the random oracle. Yes, let's start. The IBC is the proof system for the repeated computation, like the ZKVM. Then IBC is defined by the 4 algorithm, the parameter generation and key generation, and IBC prober and verifier. IBC prober update the new proof from the previous proof with the output of the step function. And IBC verifier verify the IBC proof and output the accept or reject. IBC proof pi guarantees the two things. One is the previous the where computation of the step function in the previous step, and next is the where verification of the previous steps. From the two facts, the IBC proof pi guarantees the final output is from the initial input Z0 to ith repeated computation. And I will please check the folding scheme. Folding scheme is a kind of aggregating proof technique. Let's consider the 2 proofs, the pi 1 and pi 2. And after the folding, then one proof. Then one proof large pi implies the small proof pi 1 and pi 2 belong to the sum relations. And the folding prober and verifier can be described as this. The prober takes the 2 proofs, and the folding prober output the folded proof large pi, and proof for the folding pi fold. And the folding verifier takes the instance of the proofs U1, small U1 and large U1, with the proof for folding pi fold, and it output the updated instance, folded instance. Then verify pi 1 and pi 2 using the folding scheme. Then the interchange this. The verify the pi1 and pi2 separately to the verifier one proof pi. And this is the description of the NOVA. So let's consider this situation. The 3 repeated step function, initial value is G0 and the final output is G3. And then in this situation, let's consider the bonding verifier. Bonding verification with the initial input, and at the first the IVC prober output the probe. U1 W1 is the RNCS of the F prime and F prime circuit, and large U1 W1 is the initial bodied setup, bodied probe. And next IVC prober first run the bonding probe with the small U1 W1 and large U1 W1, and from the input and output of the bonding probe, the IVC prober run the bonding verifier, and then and later the IVC prober generate the RNCS of the F prime, small U2 and W2, and similarly repeated this way in IVC prober, and then the verifier check finally the small U3 and W3 and large U3 and W3 belong to the relation, and the IVC should satisfy two properties: the completeness and knowledge soundness. The completeness is that let Gi is the output of the step function, and the V and the prof pi I is passed to the verification, and let the prober algorithm run with that input. Then completeness said for any constant I, the following equation holds. That means with the valid previous values with probe, then the IVC prober generate the valid next probe. And the IVC knowledge soundness is I described the attack game of the IVC knowledge soundness. First, the setup, the parameter lambda and constant n, then the adversary p star take the public parameter and output the step function and initial G0 and the final output G and IVC probe. And from the adversary output, the extractor takes public parameter G0 and G and output the local inputs, sequentially local input omega 1 to the omega n, and then from using them and G0 can reconstruct Gn. Then the attacker succeed if the G is not equal to Gn, but the verification the probe passed the verification. Knowledge soundness said the attacker cannot succeed with a high probability. Then how large is the constant n? In NOVA, step n is the most poorly logarithm size of the security parameter, because the reason is the probe issue for extraction. The running time of IVC extraction is 2 to the O(n). So then is the definition of knowledge soundness sufficiently for sound IVC? Yeah. I will answer about that in this section. Yes, I'll give a variant of augmented executions. Let's consider the function f prime takes the additional bit. The bit decision the mode of the computation. If the bit B is 0, then I consider the abnormal mode, that is skip the step function. If the bit value is 1, then not skip and normally running of the step function. And let's consider the two type of the IVC prober. IVC prober P0 is the IVC prober for the abnormal mode, B equals 0. IVC P1 is IVC prober for the normal mode, B equal 1. Then IVC construction, let's consider the IVC construction using the F prime. Then the verifier accept both mode because of the F prime, the RNCS of F prime contains skip and normal mode, so the IVC verifier accept both mode for the RNCS prop for F prime. But this construction has the soundness issues because let's consider the simple example. First IVC prober run the P0, and second IVC prober run P1. Then the IVC verifier accept the large pi 2 because of the verifier accept both modes. So the prober does not matter. However, the binary output G2 is not equal to the twice running of the step function F. Then how to add some additional variables? Let's consider the additional variable yi. Yi is defined as the initial value is 1, and if the bit is 1, then the yi is updated to the scaling of the previous one. But if b is 0, then yi is the hash value of the previous value, and where the hash is the random marker. Then IVC verifier additionally, and then we give a IVC verifier to ability to check the y, and then IVC verifier additionally check the y1, and then if IVC P1 is run for all n step, then no matter because of the all step, the y value converts to 1. So the IVC prober P1 with the IVC verifier satisfies completeness. And I'll call this scheme Nova IVC with this execution set the epinema Nova. And let's consider the number theory trick. This is needed for the resoundness proof for the epinema Nova. Let the prime p be a lambda plus 1 bit, then within the 2 to the lambda to the 2 to the lambda plus 1, and let t is less than half of lambda, then the probability is negligible, 2 to the half of lambda. The proof sketch is this. This is simple. Degree 2 to the t polynomial has n most 2 to the t zeros. Then the probability is, you can check this simple probability equation. Then let's consider this case. At first, the IVC prober P0 running, and at the April then, the only prober 1 running the last n-1 step. Then let's check the yi value. First, y1 is the random element of the field. Then y2 is the scale of the y1, and y3 is the scale of the y2, and so on. So then yn, then the IVC verifier check the yn is 1 or not. But however, the probability of yn equal 1 is negligible by the number theory tricks. So the IBC verifier can detect the abnormal mode within log previous step. So the abnormal nova is satisfied noise sound needs in noise sound needs. However, let's consider the more steps. Then consider the lambda plus 1 prime with the form p is 2 to the lambda plus 1. Actually, the maximum lambda of this form is 16, so very short. But so in paper we use the proc prime. P is alpha times 2 to the t plus 1. There are many proc prime. But for the sake of simplicity, I will explain this type of the prime to the lambda plus 1. By Fermat's theorem, the x to the p minus 1 equals to x to the 2 to the lambda equals 1 for all non-zero elements. If n is larger than lambda, then all non-zero x, the value should be 1. Then let's think about the previous slide and this slide. This is the similar situation, but the yn should be 1 because of this property. So the IBC verifier accepts the prop pi. However, the f to the this is typo. The n plus 1 is not n plus 1 should be fixed n. Anyway, the IBC verifier accepts the prop, but the f to the n to the input g0 is not equal to the g, the adversary, output adversary. So the epinormal nova satisfies the completeness and early soundness, but the observer in the linear step. So is the early soundness definition sufficient for non-observer IBC? Our answer is no. So I have to point out the early soundness should be fixed like this. The early soundness should cover the linear step, polynomially large step. However, the nova does not satisfy the revised definition in standard model. However, the original nova IBC does not have concrete attack, so we hope to analyze this nova in these definitions. So that's why we consider the analysis model for group-based schemes like nova. First, let's consider why the blow-up issues occur. The proof of nova early soundness is this. Simply say, to extract the omega I minus, to extract the IBC extractor should output the local input omega 1 to the n, and in nova use the technique, the partial extractor output. EI output the omega I, and EI minus 1 called the EI. So simply say to run the EI minus 1, then the E minus 1 should be called the EI 2 times. So from this inequality, the running of the extraction is exponentially blow up. So how to avoid the blow up issues? Our answer is avoiding using folding adversary extractor for the IBC extractor. and the straight line extract is needed. So we consider the model for groups, the general group model and algebraic group model. General group model is an idealized model where all group operations of adversary are carried out by making oracle query like this. The adversary query the oracle, and oracle says the encoding of the A and B. And adversary wants operation between operation of the sigma A and sigma B. Then query A plus B and receive the, okay, sorry. And this is an algebraic group model. Simply say the algorithm output the group element, then it should provide their representation, like this. Then this is the structure of NOVA, and I want to set the limitation of GGM. The extraction procedure says is this. From the group element UI, their representation is WI, because the extract WI, and from the WI, retrieve the UI minus 1, and so on. But group element UI minus 1 should instantiate it to a field element in vector WI. But in GGM, hard to describe the instantiation because a group element is like a random bit string in the view of the adversary. So we use the algebraic group model, but should make clear the action of the algebraic group model. Consider the algebraic adversary output the proof, then explicitly the WI is not a group element. However, the WI contains group encodable part UI minus 1 in the NOVA boarding schemes, in NOVA construction. Then should algebraic adversary provide a representation of UI minus 1? Our answer is yes. Due to the RNCS constraint, WI contains group encodable part UI minus 1 if pi I is valid pro. So, this is the clear of the algebraic adversary, and I think it can be skipped. It's the other. So, I'll treat the NOVA knowledge soundness proof and conclusion. If the IVC adversary outputs the accepting proof pi n, then it also outputs the representation set R, because the adversary is algebraic. By accepting proof pi n can get representation the Wn-1 and Wn-1 small and large of the instance UN-1 and large UN-1 from the representation set. But in this page, we should guarantee that the representation is indeed witnessed. But the non-interactive boarding schemes knowledge soundness guarantees the representation are indeed witness of UN-1 and Wn-1. So using the extraction recursively get a previous proof. So from the proofs can extract the find the local input omega 0 to n-1. So but this process can do polytime, although the step is linear or poly. So NOVA is a poly-step knowledge sounds in AGM. So this is the conclusion. First, we give a four-jumper IVC that satisfies the knowledge soundness. The definition, so we point out the definition of knowledge soundness should cover polynomially large step. And second, we prove the poly-step knowledge soundness of NOVA in AGM make a clear rules of algebraic adversary and propose weaker condition for hash, but is not strict this presentation, sorry. So, due to the first one, we should consider the strong requirement, but by supporting the algebraic group model and hashing, we can prove the NOVA is down. Yeah, this is the end of the presentation. Thank you.
Okay, questions?
Hey, more a remark than question, since you didn't have time to get into it. I wanted to say I really like the zero testing assumption, which is basically saying it's hard to find a polynomial that the hash will map to its own root.
Yeah.
So I just want to say, since you didn't have time to talk about it, that I thought it was really nice. I really liked it.
Oh, thank you.
That was Ariel, if you didn't see in the streaming. Okay, more questions? Two more questions. Here and then here.
Hi, thanks for the talk. Do you have any ideas about how to construct such a hash function with the zero testing property?
Actually, I do not think the concrete hash function, but if the hash function satisfies this property, then we can prove the resoundness of the NOVA in algebraic group model. So in paper, we show the theorem. If hash is a random oracle model, then the hash satisfies our given property, general zero testing property. But do not consider the concrete hashes. Sorry.
How would the security result in the random oracle model be situated with regards to Valiant's conjecture, which says some impossibility results for IVC in the random oracle model, I think with different assumptions, but I'm wondering how you see these two results as relating to one another.
Actually, in NOVA, the random oracle should be instantiation in the circuit. So some people think this random oracle instantiation is too strong. So we hope to relieve the strong condition to this property.
But doesn't the random oracle model imply that a hash function with this property exists? So impossibility in the random oracle model would imply impossibility with such a hash function?
So the hash satisfies the theorem said if the hash function satisfies the random oracle, and not attack, satisfy the random oracle property, then the hash also satisfies the general zero testing. So the zero testing, this general zero testing hashing is the large set inside the random oracle set, I think.
I think that makes sense. Thanks.
Okay, round of applause. Thank you very much.